guys, I'm going to go over the bit about ionization energy from today's class, as well as the slides that we didn't quite get to. This is a really important concept, so I want to make sure that you can go back and look at this again to review it. So again, ionization energy is the energy required to remove an electron. Okay, so the amount of energy required to remove this electron from this atom is what we refer to as ionization energy. So if we look, this particular atom is hydrogen. It has one proton and one electron. So the positive represents protons, the negative represents electrons. So the force of attraction between the positive proton and the negative electron are what hold the atom together. If we want to pull these apart, we have to interrupt that attractive force. We have to break that attractive force. So that requires an input of energy. So energy has to go in order to remove an electron. So to remove an electron, there needs to be an input of energy to make that happen. Okay, so a zap of energy. When that happens, we can express that as a reaction, right? So the hydrogen atom plus energy is going to give us a hydrogen ion plus a free electron. So then, if we take a look, here is helium, and the difference between helium and hydrogen. So hydrogen has one proton, one electron. When we go to helium, we have two protons and two electrons. Can you guys hear the rain? It's pretty loud. So in this particular case, we've increased the magnitude of charge by a factor of 2. We went from positive 1 to positive 2 center, and we have two negatives. Okay. So the other difference between hydrogen and helium is that helium has two electrons to remove, okay? So we're going to have two different ionization energies, one for the first electron that we remove and one for the second electron that we would remove. So helium plus energy is going to give us helium positive plus an electron, okay? So our products are going to be this helium ion. But there's still an electron to remove, and that's what we're going to call our second ionization. So we have our helium ion plus energy is going to give us helium-2 plus, and we've removed yet another electron. So that's going to be our second ionization energy. So which of helium's ionization energies would you expect to be larger, the first or the second? So what we need to look at is when we remove this first electron here, this first electron is attracted to these two protons in the center. However, it's also repelled by this second electron. So when we remove this first electron here, there's a little bit of repulsive force from the electron that is right here. Once this first electron is gone, we've got the two positive protons and one electron. There's no longer a repulsive force from an electron, so now we have a much stronger attractive force remaining. So which one would have a higher ionization energy? So the greater the force of attraction, the more energy required to remove that electron. So there will actually be less energy required to remove the first electron than the second. And that is always true for all of our electrons. The first electron requires the least amount of ionization energy, and each consecutive one is going to require more ionization energy to remove it. So if we look, these are actual measured amounts of energy required to remove those electrons. So EV stands for electron volts, and this is a measurement of energy. So to remove the first electron, the first ionization energy, so IE stands for ionization energy, takes 24.6 electron volts. To remove the second electron, so the second ionization energy, takes 54 electron volts, almost twice as much. Okay, and that is because that repulsive force between these two electrons will no longer be there. So here's lithium, and lithium, in addition to having an additional electron, now has another energy level, right? So N equals 1, N equals 2. We have 3 protons in the center of our atom, and we have 3 electrons. So this time, when we look at our first ionization energy, that ionization energy is really small. It's 5.4 electron volts. And so there's a couple of reasons. So talking about Coulomb's law, there's a couple of reasons for this. One, we can see that the distance between this electron and the nucleus is much further than the distance was between this electron and the nucleus. Okay, so the distance is further, and we know based on Coulomb's law, the greater the distance, right, the smaller the force of attraction. So we have a greater distance, okay? The other thing that we have going on here is we have what's called shielding, okay? We have interference of this positive attractive force by these two negative electrons here, which are going to be repelling this electron. So earlier when we were just talking about Coulomb's law, that is that scenario where we have our electrons all in a row, right? So we had that diagram that showed we had the three positives, right? And then in between, we had two negative particles, right? And then we had this negative out here. That's the same scenario, right? We have these two inner electrons, these two negative particles that are repelling this outermost electron here. And so what these two electrons do when they shield, right? They're canceling some of our positive charge, right? So what we end up with is an effective nuclear charge of +1. Right? Because these two negatives are going to be canceling these two positives. So what's left over is the effect of just one positive proton on this electron, and it's a much further distance away. So because of that, the first ionization energy for lithium is going to be much lower than the first ionization energy was for hydrogen or for helium. Okay, so that 5.4 electron volts. Then when we go and look at our second ionization energy, what you're going to see is a pretty big jump. Hey, there's some thunder. It goes from 5 to 75. That's a huge jump in ionization energy. And so let's think about Coulomb's law as to why that is. So we remove this electron, and now when we go to remove this one here, we have no shielding, right? This electron had shielding from these two electrons here, so no repulsion from additional electrons. And it's going to have an effective charge of 1, 2, 3 positive charges, because again, we don't have anything in between to cancel out some of that positive charge. So the effective nuclear charge on these two electrons is going to be +3, whereas the effective nuclear charge on this electron was only +1. And so therefore, we have this big jump. Whenever you see a large jump in the energy, or in the ionization energy, this oftentimes will tell you that this is what we call a valence electron. So valence means outermost electron, and that's spelled valence. So this would be a valence electron, and then these guys on the inside are what are called core electrons. Okay, so valence electron versus core electron. So these are both core, they're on the inside. This is a valence. When we look at hydrogen and helium, neither of them had any core electrons. And then when we go and look at the third ionization energy, again, they're both in the same shell, so relatively the same distance and same positive effective charge from the nucleus. So they're about in the same range, not quite as big a jump. So it says, how would the first ionization energy of hydrogen compare to the first ionization energy of helium? Explain your reasoning using Coulomb's law. And so when we're looking at helium versus hydrogen, hydrogen has just one proton in the center. Let me keep with the colors. Protons, we were making blue. So the protons, there's just one of them, right? One proton for hydrogen. Whereas when we're looking at helium, we have two protons. Okay? Then when we look at the electrons, helium has 2 electrons out here. Whereas hydrogen only has the 1. Okay? So when comparing the sizes, and I drew these pretty horribly to show that they're the same size, they're relatively the same size across. So the distance between the nucleus and the electrons are pretty close to the same. What is different is our magnitude of charge. We have a greater magnitude of charge. Okay, and so because there's a greater magnitude of charge, there's a larger attractive force, right? So between these two, there's a larger attractive force. Okay, so there's a larger attractive force between our first electron and the nucleus than there would be over here in hydrogen, okay, because the magnitude of charge is smaller. The magnitude of charge is 1, whereas the magnitude of charge over here is 2. It's double that. So it says, explain your reasoning, and so compare the first ionization energies. So here's our reasoning, and so helium would have a higher first ionization energy. Higher or larger first ionization energy. IE means ionization energy. And the reason again for that is it has a greater magnitude of charge, larger attractive force, CE. So a larger attractive force, therefore it's going to have a higher first ionization energy. It requires more energy to remove that electron.